Today I'm going to talk about, I'm going to start introducing state space. So in the previous lectures we mostly talked about transfer functions and how to go from a system of equations and reduce those using linearization into a transfer function. And then analyzing the stability, analyzing some time-specific requirements, some frequency-specific requirements such as phase margin, gain margin. And now I'm going to transition over into a state space. And so in so doing, I'm going to talk at least initially about some of the differences between what would be useful in a transfer function setting and what would be useful in a state space setting. So, as we remember, a transfer function is given by this function here. G of s is equal to this the product of a bunch of poles, or zeros rather, on the numerator, over the product of a bunch of poles, and these dictate the stability of our system. Right. Oops. And right. So there's a number of advantages for using transfer functions in analysis. And so I'll just kind of list them and talk them through. So some advantages are, well, they're easy to use. For small systems. And in so doing, you can easily look at the dominant features of a transfer function and use those approximations for analysis. For instance, using the dominant poles to do an analysis for a controller. So another thing that's nice to use transfer functions for is if you're dealing with more of a black box system where you don't necessarily know all of the parameters inside the system, or even what the system what the systems are doing it themselves. So this makes transfer functions easy to use. Maybe I'll do this. They're easy to use or estimate from pure data sources. And this could be through a Bode plot. Oops. There you go. Bode plot analysis. Or either step response, or other signal, which is no more than a Bode plot for frequency and responses, or other signal response. So what am I saying here? I'm saying that given some input and some output, so we got U of t and Y of t, we can say that our black box here satisfies some G of s, which is a transfer function. So now your goal is to estimate what this transfer function is. And lastly, number 3, it's good for frequency response analysis. Good for Namely, when I give some frequency, when I give some frequency in, I expect some frequency out. And there's a lot of applications that frequency response is really useful for. On the other side of that, there's a lot of there's some disadvantages to these types to transfer function analysis. The first one being that it's really only good or helpful to use them with SISO tools. So only good for single input, single output systems. And that's what we've seen so far. There is ways to extend it to multiple input, multiple output systems. But it ends up just being a matrix of a lot of transfer functions. And so then you analyze each matrices individually. It doesn't really lend itself well to complex systems. Or nonlinear systems. Which is why we used, at the beginning of the class, we used linearization to take out those nonlinearities and look at transfer functions in state space around an equilibrium point. And lastly, sometimes you want to look at what the internal state's doing in a system through different techniques. You can estimate the internal state, so typically we measure the plant, but those measurements aren't necessarily the state of the plant, right? So for instance, if you're using a thermocouple to measure temperature, your output is actually a voltage, not the temperature. And then there's a transfer between what the temperature is actually and what the voltage out that you're reading, right? So in so doing, it's not trivial with transfer functions to apply state estimation techniques. Like Kalman. All right. So on the other hand, let's go to a new page. On the other hand, for state space, so state space is, in general, given by these equations here. X dot is equal to some function of x and u. Okay, and this is in continuous time. Or y, and the output y is equal to some function g of x and u. So these two things coupled are the state space equations. And notice two things immediately, right? So one advantage is that we can consider nonlinear systems naturally. Now, we won't look at nonlinear systems necessarily in this course. There's a slew of graduate level courses that you can take that delve deep into nonlinear systems and all the techniques and intricacies on designing controllers and filters and reference governors and different sorts of applications using a state space equations that are not necessarily easy to use to do in that frequency domain. Another thing is, if you notice here, we have x and u. Here we have x and we have u. We say that x is in Rn and u is in Rm, okay? So these are real numbers. Note that R is the set of all real numbers. Okay, so we can use both SISO, consider both SISO and multiple input, multiple output systems. Another thing that makes state space domain analysis a little more accessible is that we work directly with ordinary time. T. For continuous time systems. So for but us as humans, we're a little more apt or able to deal with systems that deal directly with ordinary time than we are with frequency time, which can be kind of nebulous. Another advantage is that we can design state estimators. To build our controllers off of. Alright, so what do I mean by that? So again, if we have this thermocouple, thermocouple is measuring the temperature, right? But its output is a voltage. So now if we can do one of two things, is we can take that voltage and know a voltage that we want to apply to say a pot of water, right? Say we need a pot of water to boil. Say we're making a beer, right? What you need to do is you need to have your wort, your mixture, boil for a certain amount of time at a specific temperature. And if it goes above a threshold, it kills all the fermentable sugars, right? So you can't let it go above this temperature. So you can design a controller to either accept the power input that you need to make this pot of water go to that temperature and compare it to the voltage on the output, right? Or you can take the internal temperature directly by estimating it using the voltage, right? And now you say your reference temperature is the temperature that you need to be. I think it's like 170 degrees or something like that. It's been a while. But so now instead you can take the estimate and compare it to that reference and then drive that power input that you want. Okay? So that's what I mean. So that doing that is a state estimator. Okay? Converting the voltage measurement into a temperature, right? Knowing the dynamics of your system, knowing the output matrices and conversions, you can do that quite easily. And that's pretty simple to do. Okay. And there are some. I mean, I'm not gonna to lie. There are some disadvantages to this. Dealing with state-space systems, yeah, they're built on physics and dynamics, but really, when we're talking about LTI systems, they're just matrices, and so they can be kind of not necessarily intuitive. Right. Another thing is when you're making these systems, the simulations can be pretty complex and large, and difficult to handle. So whereas in transfer functions, when you're doing a Bode plot, you're looking at the basically the response of your transfer function to almost an infinite number of frequencies, right? Whereas if you wanted to do that with a state space system, then you're going to have to simulate it for each one of those frequencies. Well, that's one way to do it, is to simulate each step response. You know that the general system is going to be stable, let's say, but you might have it where there's some differences between each frequency that you're simulating. So that's one big difference, is you may have to run simulations numerous times to be able to validate your results. Okay. So that being said, that's the main differences between a transfer function. Well, the main advantages and disadvantages to using a transfer function versus a state space system. So in the rest of this course, I'm going to be talking about linear time invariant systems in particular, okay? So let me just write that. We will be working with linear systems. Okay, and so as we discussed a couple times in class, linear systems, and I'll talk about the properties of linearity in the next presentation. But linear systems are typically given by the following equations. Make this bigger. There we go. All right, so we get the first one, say x dot of t is equal to ax of t plus b. This should all look familiar to you, right? Bu of t. And the next one, y of t is equal to c x of t plus du of t, okay? Or we can consider the same thing, x dot of t, but the matrices A and B are functions of time, okay? Likewise, the matrices C and D are functions of time, okay? So now, to distinguish these, we call this one linear time invariant, or LTI. And this one, on the other hand, is linear time, what do you think? Variant, right? Or LTV. Okay. And so the main differences, so which are typically determined by the system or linearization techniques applied. So remember, everything in life is nonlinear. It's through our assumptions and our modeling. Now we take those nonlinear systems. Drop my pen. Now we take those nonlinear systems and we reduce them down into something that we can apply these linear systems tools with. Because again, deriving controllers and analysis for nonlinear systems is very complex. So these systems in a block diagram they're given in a block diagram the linear time system are given, actually let's just do an LTI system, are given by, alright, so let's see if I can do it on this. So we have a reference, and then that goes into our controller gain, K, which goes into our input matrix, B, and this is going to push into X dot, a summation block, which the result of which is X dot. That goes through an integrator, which gives us X. That comes around, multiplied by A, right? So that's the feedback there, gives us X dot. Then that X runs through our C, the output matrix, which gives us your output. And that's fed back to compare to the reference. Minus plus. Right, so if we had a LTV system, a linear time varying system, then we would have a clock out here, time, which goes into each one of these blocks. And then A, B, and K, and C may all be defined by this clock here. And I'll talk a little more about what the difference is between an LTV system and an LTI system in some more numerical terms. But that's all I have for you for this short presentation. Stay tuned for the next one, where I think I'll talk about some properties of linear systems and linear time invariant systems in particular.